Good evening, and thank you very much for coming tonight. It's our honor tonight to have Dr. Phallab Bhattacharya. We are also delighted to have one of his former students as one of our professors here, and I thought it's most befitting that I would request Dr. Wade and John, who is the professor in electrical engineering, to do the introduction. So please welcome.
Well, thanks, Annie. Yeah. Well, so definitely it's my great honor to have.
Our time back then.
In fact, I prepared a few slides with me, but Dan said it's too late for me to show anything on the screen, so I will just say a few words here. Well, definitely, I would say the first thing I would say definitely is a life-changing event for me to be part of the group. Professor Bhattacharya, I guess, graduated from the University of Sheffield, and he's been faculty in Michigan since 1980 or something? I don't know the year.
1983.
1983, yeah. Well, I joined the group in 1997 and graduated in 2001, and I came to UTA 2004, where I work on the photonics area. And actually, some were discussing in the UTA, we have over 20 faculty in the photonics area. So we're hoping to build momentum, and also we are very delighted to have Professor Bhattacharya to here give a really distinguished lecture as part of the College of Engineering lecture series. As I said, I prepared a few words, try to introduce or say a few words, but I didn't have my slides, I didn't have my cheat sheet as well. What I can remember is I tried to say it a different way. You guys saw the CV, impressive, sort of abstract, so I will not repeat that part. I was thinking, from a formal student point of view, what kind of professor he is as a person, right? So I thought about a few words actually. So I thought I use the 4 letters just quickly, STM. Okay, that's it. Well, with a STEM, right? Science, technology, engineering, and mathematics, right? That's very important. So I think the S, I think is really scientifically visionary. That's my words to say. Basically, I think Professor Bhattacharya is one of the pioneers in nanotechnology. He actually, I say that he has a very solid foundation from physics point of view, and then be able to see, I say see before others can see. So really that's the vision. And actually, the second part is very important in the area is technology. So it's a really technological leader in the world. And he made lots of contributions. I have a list that shows awards. All the major awards across the world in the field of compound semiconductor, low dimensional materials, quantum doors, nanowires, as well as, of course, integrated photonics, optoelectronics, lasers. You can list going on so many different things. Makes things happen.
Can I start?
E for educator. He's a very inspired educator. In fact, I'm the number 41 in his group as a PhD student. Now the number is 75. I believe probably very soon will approach additional more numbers there. So definitely impressive. And most of them are really in the different areas, lots of universities, And with the STE, last one is the magician. To make impossible possible. Really, actually, some of the things many people did many years couldn't make it happen. Physics, material science, but Professor Bhattacharya made things happen. There are lots of things going on, very exciting. So, without further ado, I don't want to take too much time. Let's hear some part of his exciting work. Thank you.
Well, Vedant, thank you very much. I was nervous as to what you were really going to say. But it's an honor and a pleasure to be here at UTA. It's my first visit to this campus. And so I'll try to do justice to all this and give you a glimpse of what I do, what we are doing currently. In some of the, I think, fairly important areas of science and engineering. And so let me see if I can give a flavor of that. That'll be doing some justice to my students who really work so so hard. I thought, as a general talk, I'll get started. I don't do this very often, but I thought I'll give you a glimpse of our facilities. Where we make all of it happen. So we started, we moved into a new building in 1986 when everybody was moving from, all the engineering departments were moving from, this move had started in the early 80s from Central Campus to what is called North Campus. And electrical engineering was the last department to move because it was the largest and we needed a larger building and so on. So at that time, when this building was being constructed, we decided that we should have a decent clean room and start microelectronics research. Michigan was known for microwave research and so on, but really there wasn't, before I went, there wasn't too much of work in microelectronics as we know it now, which involves materials, crystal growth, device processing, and the whole works, integrated circuit, optical integrated circuits and so on. So that facility, we built a 6,000 square foot clean room at that time, and we were the first in the nation to do something which a lot of people told us that it was a ridiculous idea, it wouldn't work, and that was to put all silicon processing and compound semiconductor processing under one roof. Of course, we had separate bays for different kinds of work, but it was the same space, airspace that we shared. And it really has worked now, and it became the model for many other such nanofabrication centers around the country. Around 2006-07, we got some extra funding from the Lurie Foundation, and we expanded that, and this, what you see is the expansion part. The older part is in there in the building. So now what we have is a 13,500 square foot clean area, 10,000 class clean rooms, and we really have all the major facilities that is required to do state-of-the-art microelectronics and optoelectronics research. And this is, these are some of the pictures of the shells. You can kill the light in front. Is it possible at all? And this is before it got equipped and so on, but now it's all buzzing with activity. And I won't go through this, but it really does have all the facilities that we need to do processing down to a few tens of nanometers. Starting in 2004, it's been now a decade, we with 13 other universities, we form a part of the NNIN, and this is funded by the National Science Foundation, and our charter, of course, is to provide fabrication, characterization, and computational capabilities to anybody that comes as a customer. So we have very open, shared facilities, and one of the important aspects of it, which we always had, was this very high level of staff interaction for instruction and project support. And this we had ourselves all the way back in 1986 when we opened this clean room. We decided that we were going to run an industry-style microelectronics processing facility, but in a university. And that was a difficult thing because the university has its own culture, industry has its own culture, but we made it happen, and it runs 24/7. We have a huge number of technical personnel, and they are, I've seen it myself, even on Christmas Day, if there is a problem in the lab, they will come and fix it. So, but the other part of this, which is very important, is the environmental health and safety programs that we have as a part of this, and programs in education outreach and social and ethical issues. For example, we go periodically and regularly to inner cities in Detroit and so on, and we try and bring the high school students to us and get them motivated and so on and so forth. So that's also part of the program. Um, we have 90 active groups using this facility, and this is the rough sort of breakup. 65% of that is internal users from the university, and these are all the departments. And then there are the external users, small companies, large companies, other universities, even foreign entities, and so on. So the place is busy. So now coming back to my own sort of domain and research. So it's in my research, I go all the way from materials. I was trained in crystal growth myself 40 years ago, and I've been doing crystal growth ever since, using different techniques. Back in those days, we used to do liquid phase epitaxy. Now we do more sophisticated, use more sophisticated techniques like molecular beam epitaxy, and it's a controlled evaporation system. Well, we have an expert sitting here. And it allows us, it gives us tremendous precision in controlling layer thickness, growing all kinds of very fancy and sometimes very novel structures and nanostructures. So I have different systems, there are 3 of them, and for growing different materials, different kinds of materials. Even in the nitrides, we have these 2 systems, and I use one to grow heterostructures and quantum dots, and I'll show you what they are. And the other one, we grow nanowires and those kind of things. And then there's the arsenide system, and so on. So it was important for me, and this is what I learned as a student back in England, that if one has to do microelectronics or optoelectronics, one has to have a very, very strong materials capability. Without that, you just can't do it. And if you look around here also, you see places like Illinois, Stanford, Santa Barbara, and all that, they have very strong materials capabilities. It gives you that additional degree of freedom to explore, to experiment, to do all kinds of things, and it's a wonderful training ground for students. So currently, I mean, I've gone through all kinds of many lives and many things. I mean, I've done microelectronics, I've worked for several years. I've worked on transistors, high-speed transistors, high-frequency transistors, and all that has come in useful for things I've done later. I worked with silicon, germanium, 3-5s, and now mostly with the III-Nitride materials. So, as I said, we do molecular beam epitaxy, and not just to grow devices and make devices, but really do material science. We do very serious material science with what we grow. And then, of course, the application areas with the nitrides, we're making visible lasers and LEDs. Now, you may say everybody's making visible lasers and LEDs, but you'll see we do some things which are very different. And these nanowire lasers, which happened almost as an accident. And then I'm looking at some little far out areas, non-classical light sources, and one of them is single photon emitters. These are becoming very important for quantum cryptography, quantum information processing, and all that. Single photon emitters have become very, very important now. And then this last one is sheer fun. It's physics, and of course now I'm taking this physics to the engineering domain, and it's a very new kind of coherent light source. I mean, for the last 50 years, we've known the laser, the semiconductor laser, and now there's this new entity based on a completely different principle. These are called Polariton lasers. So, with that, maybe so I'll give you a little bit of an introduction, and these are some borrowed, couple of borrowed view graphs from colleagues around the country. But gallium nitride, and I was one of the, even doing materials research and so on and so forth, but I was one of the last people doing epitaxy to get into the nitrides. And in fact, for many, many years, I was convinced I was not going to do anything, have anything to do with the nitrides. And it's because I just didn't think I had the mental bandwidth to handle another new material, and so that was one factor. The other factor was I naively thought that everything that can be done with the nitride is already being done. So Shuji Nakamura and company, they are doing the LEDs. People like Umesh Mishra and company, they are doing the high frequency, high power transistors. So what is left? Well, all that changed when, and this is true. Our chair, some years ago, not that many years ago, walked into my office and I said, well, and said, well, I have $1 million for you. You can do whatever you want. It happened to be the 1st of April. And I thought, and I said, Dave, is this a April Fool's joke? Can you go back to your office and send me an email? And which he did promptly, and he knew this was real. I never asked, I dared not ask anyone why this good fortune befell me, but I quietly took the money. And of course, as everybody had predicted, I bought another MD system, and then that's when I discussed it with my students. And said, so what shall we do with this? Or what kind of a system should we get? And they suggested, well, maybe you should get into nitrides. So that's how it happened. But then as we brought this system up, I was scanning through the literature and all that, and I immediately it was obvious to me that there were all kinds of things that was still not done. There were problems that had to be solved, and so on. So let me tell you a little bit, a bit of a background from a materials point of view, and this is going back in history. Some of you will be able to relate to this. Back in the 60s and 70s, when semiconductor research became important after, say, the invention of the transistor, and it was mostly silicon, germanium first, and then silicon, and then gallium arsenide. And most of the research was being done at Bell Laboratories and a few universities. And there was an army of very talented people who were characterizing these materials to death. So any parameter, any material property you want to know of gallium arsenide or indium phosphide or silicon and so on, you have it. You just have it. With gallium nitride, the history is very interesting. Well, you know, I mean, even at Bell Labs, people like Jacques Pankove and so on, they realized in the 70s that this was an important material. Its band gap fell in the visible part of the spectrum, and so it would be important for displays, for a multitude of other applications. They just could not synthesize the material. It wasn't, the techniques were not developed, and people forgot about it. For years, for decades, people forgot about the nitrides, and you know, other semiconductors became important for fiber optic communication, high-speed transistors, and so on and so forth. Till, again, there were some pioneers who took it up again, and Nakamura's story, and most of you I'm sure don't know how he got into this, but I have seen it firsthand. So, but anyway, I won't get into that. But there were these three pioneers, Professor Akasaki and his student Hiroshi Amano back in Japan, and also Shuji Nakamura in Nishia, who relentlessly, you know, solved all the materials problems and made it happen, and that's why we got the Nobel Prize last year. But what happened after that was there were these two groups who ran with it, and it was very device-driven. Nakamura ran with the, you know, well, they were developing the LEDs, and so was half the rest of the world, and the other half was doing the transistors, and nobody had the time to really look at the fundamental material properties. Now, one of the problems of looking at the material properties was this material is very heavily dislocated. Even when you grow gallium nitride on gallium nitride, the substrates are not as good as gallium arsenide substrates. So they have 10 to the power 6 per centimeter square defects, and you just have to live with them. And nobody ever thought, it was a mystery why that gallium nitride even give out light. We now know why it gives out light. But, so now it's a $10 billion industry and growing. I mean, hopefully most of us will see in our lifetime that every city or almost every city in the world will be lighted by solid state lighting. And then there is this other application, the high frequency. So, you know, most wireless base stations, RF stations and all that, and gallium nitride is the material of choice and not silicon carbide, although silicon carbide was developed earlier. and the DoD for sure is betting on gallium nitride, and they're putting all their eggs in that basket. And it has, in spite of the dislocations and all that, it does provide some inherent advantages, and that's why we can use them. And one of them is this: it has a very tight lattice, and there is no shear stress in the C plane along which we grow, and in this direction there is no shear, and so these dislocations don't move, and that's what makes the material very interesting. From a person like me, my point of view does optoelectronics, the nitrides have other very exciting advantages, and one of them is this large exciton binding energy. So compared to gallium arsenide, which has only a binding energy of 4.8 MeV, and these are some of the other. Gallium nitride, as you can see, in bulk form, it has about 30 MeV, and in quantum confined structures, it's about 50 MeV. What it means is that the excitons survive even at room temperature, and so you can make excitonic devices at room temperature, which you cannot do with gallium arsenide. And here are some nanostructure devices, which I'll briefly talk about later. These are single photon emitters using nanowires in my group and in other groups and so on. So this large oscillator strength, in other words, a small Bohr radius, which leads to the large exciton binding energy. But also, when you grow heterostructures, the band offsets are very large, which means that the electrons and holes can stay confined and they don't jump out of the recombination regions in LEDs and lasers and so on. Just a short primer. So these are hexagonal crystals, these three nitrides, and you can see that they are smack in the middle of the visible range. So one uses these alloys, indium gallium nitride, to get all the visible colors. And that's the nitride system in more detail, the binaries and then the ternaries and quaternaries in between. And so it's a hexagonal structure, and these are some of the fundamental properties. And just to give you a calibration, a 3-inch gallium arsenide substrate costs $200, a 3-inch gallium nitride substrate costs $5,000. So there is this drive to be able to make and grow devices, commercial devices, on other substrates, and that is just sort of a requirement with the nitrides. Though we can get gallium nitride substrates, but they are horrendously expensive. And if they are expensive, it's just because of the phase diagram and what one needs to do to grow bulk gallium nitride. But it comes with other problems also. They are in the hexagonal structure. What you have are two hexagonal close packs telescoped into each other, the nitride plane and the gallium plane, as the gallium and the nitrogen plane. And so you have they are polar crystals, so you have a spontaneous polarization. In addition, they are non-centrosymmetric, so there is a strain-driven electric field, which is the piezoelectric field. As a result, the band alignment is very funny, and for an optical device, the electron and hole wave functions don't overlap, and this causes some problems. Now, one can use other planes, crystallographic planes, like the nonpolar planes, the M plane shown here, or the A plane, where the polarization field is 0 or much smaller, but it's difficult to grow crystals on those planes. In fact, Shuji Nakamura's company, they have invested a lot in trying to grow LEDs on those planes, but there are materials problems, indium incorporation and so on, which have not been solved. So the favored plane that one grows, all the crystals are in C plane, but you can see there's a large polarization field there. And one has to wrestle with this. It causes all kinds of problems. And I mentioned the small electron-hole overlap, but it also causes another problem, a blue shift. So as you apply more bias to the device, the output frequency of the light, it changes. And that's a nuisance, actually. So in spite of all that, we have nitride based LEDs, and they are lighting the world. In all kinds of applications, outdoor lighting, indoor lighting, and I'll talk a little more about this as we move on. And the growth in LED industry has been just phenomenal. In fact, it's the only other industry that will catch up to the CMOS industry in no time and actually surpass it. So before I get back to optoelectronics, again, a couple of borrowed view graphs. One technology that the nitrides have enabled, and it's a new thing, is for power conversion. Now, power conversion can mean lots of things. It can mean voltage conversion, it can mean AC to DC, it can mean frequency and all that. So at the heart of any power conversion is a switch. What you need is a switch, and for this you need a high voltage transistor. So high frequency, high powered electronics is a new paradigm that gallium nitride has enabled, and Washington is putting an enormous amount of money in all this, simply because there are so many applications for medium voltage, low voltage, high voltage applications all over the place. So this is a gold mine, and I, including my own, I would encourage any electrical engineering department to invest in this area. So here are some borrowed view graphs. I have worked on high frequency transistors many years ago, and people in my gen can never dream that gallium nitride transistor, it's a high band gap material, could have cutoff frequencies and maximum oscillation frequencies in the hundreds of gigahertz. It's just unbelievable. And recently, actually, Hughes Research Laboratory, they reported a result of FT and Fmax of 300 and 500 gigahertz. It's just unbelievable. And at the same time, there are transistors which are good for 600 volt breakdown voltages. And the leakage at 600 volts is just 1 nanoampere per millimeter of gate. These are just unheard of, unbelievable things, but they're happening with very innovative device designs with field plates, and this is Mishra's group in Santa Barbara. Very clever designs of transistors, and that's how these things are happening. And so back to my own domain. So now, indium gallium nitride as an alloy is used to get different visible colors, all the way from violet to green and so on. Now, if you look at the band alignment of a LED, this is how it looks, and this is because of the polarization field. You have this peculiar barriers and notches and so on, and this causes all kinds of problems. One is the reduced electron hole overlap that I talked about. If you make a laser, it increases the threshold current. There's a large barrier to hole injection, and everybody knows that most of the holes pile up in the first 2 quantum wells or so on. And the wider wells and longer wavelength devices are therefore difficult to achieve. In addition, to go to longer wavelengths, one would like, after all, the real solid state white light source as envisioned, or as we all want, is an RGB, red, green, blue. We don't have that now. I'll tell you what we have. And that's because the industry does not know how to go beyond green. Even green is a struggle. They can make blue LEDs very well, but green is a real struggle, and you'll see why. And so, as you go to larger indium compositions in the quantum well, you have material segregation problems and all kinds of things. P-doping was a huge problem, and this was one of the problems that these pioneers solved, and this was mentioned in their Nobel citation. This was P-doping was one of them. But now we know how to do it, and the problem arises because in the nitrides you have an auto N doping which is very high, and the P dopants, because it's a large bandgap semiconductor, the activation energies is about 200 MeV. So all the carriers are not ionized, and the doping efficiency is very, very low. It's like if you get 1.5%, you're lucky. And then, as I had mentioned, the absence of a cheap, affordable substrate. So we grow on silicon, sapphire, whatever we can find. And then, of course, one has to live with the large defect density. So these are some of the real existing problems that one has in the LED or the electronics application world. So these are some of the problems. If you want to get visible colors, So with the nitride system, the efficiency goes down, it just cascades down, and when you reach green, it's next to nothing. Now you can approach it with other materials from the other side, aluminum, gallium phosphide. You can make red LEDs and lasers and all that, but the thresholds are very high, but that's all we have at this point in time. In the LEDs, there is this very peculiar, unique problem. The efficiency goes down. We call it efficiency droop. So if you're operating around here, you see that the efficiency has gone down by 40% from the peak. And as you go to longer wavelengths, to green and so on, it gets even worse. Then you have this shift. I had mentioned this blue shift. You have this shift as you apply bias, which you have to in a real device. The output wavelength shift. So let's say you've designed a blue device. By the time you are operating it, it's emitting some other color. And you don't want that. Same thing for the green. And then in lasers, because of this lack of overlap and so on, the threshold currents are enormously high, 10 kiloamps per centimeter square. So these are some of the current problems. So let me start with the two nanostructures that I was going to talk about. Now, I will admit that I used to go to conferences and laugh at nanowires. Simply because some of the earlier work, not with nitride nanowires, but with the arsenide nanowires, really were I knew that they were not device worthy and so on, and one could even do good material science with those. But then the nanowires, the gallium nitride nanowires came, and these were a totally different beast. So we grow them on silicon. And these nanowires grow, I won't go into the details, but you can control with the nitrogen overpressure, you can control, they're randomly grown, so they are self-organized. So the nitrogen flux controls their spacing, their diameter, and all kinds of things. But something very interesting happens. When you start the growth, you first there is a competition between the silicon-nitrogen bond and the gallium-nitrogen bond, and the silicon-nitrogen bond actually wins. And you form this very thin silicon nitride layer. Oops. And this does a lot of things. So this silicon nitride layer kind of isolates the subsequent growth from the substrate, and the epitaxial requirements are removed. So then the stress, the time-dependent stress on the silicon nitride layer forms the seed crystals of gallium nitride, and then the nanowires grow on those, and you have air atoms on the walls, on the surface, on silicon, but this surface has the minimum energy, and so it grows on that. And again, it's, as I always tell my students, that most of the time nature is trying to help you. You just have to recognize it, and this is one of those instances. So you grow these beautiful array of nanowires. You can grow them a couple of microns long. Typically their diameters are, you can control their areal density from 2 to the power 9 to 2 to the power 11 per centimeter square, and their diameters anywhere from 20 to 80 or 90 or even 100 nanometers. And you can put heterostructures and quantum disks and all kinds of things, as you'll see. So what are the advantages of these nanowires? So they have a large surface to volume ratio, so the defect density is low. In fact, this is the purest, the most defect-free form of the nitrides that one can get. And that's one thing that got me interested. That you can do not only good material science with this, but you can probably think of devices that one has never thought of. The other advantage is that as they grow, there is a radial relaxation of strain, and so the polarization fields are small. And so that's the other big advantage. And we've done, and other groups have done a lot of work. We've measured OJ coefficients, and for the first time, these coefficients agree with theoretical calculations. We've measured Schottky barrier heights. The surface recombination velocity is 2 orders of magnitude smaller than that of gallium arsenide. And of course, by varying, so you can put these so-called quantum disks, these heterojunctions of indium gallium nitride in a gallium nitride nanowire, and you'll see why we do that. And we can vary the composition of these disks, and you can get any color from violet to red. So they are very versatile. The question is, can we make useful devices with them? And just to calibrate you, so I said the nanowire diameters are about 20 to 100 nanometers, and a human hair is about 100 microns. So they are 1,000 times smaller in diameter. That's what we're dealing with. Now, we had a large program for several years with Osram in Germany, near Munich. And they also have, so nanowires are that serious, that Osram as a lighting company, they have a large in-house research program with these nanowires. But their nanowires are a little different. The ones we grow are self-organized. They grow all over the place. But theirs are patterned. They grow through a silicon mask. They make holes in the mask and the nanowires. And they are much larger in diameter. Their diameter is about 600 nanometers, whereas ours was barely 100 nanometers or less. And their heights, you can see. So they grow core shell, and this is the core with a low 5:3 ratio. So they grow the core, and as you can see, it's perfectly hexagonal. And then they come in and grow the shell in a two-dimensional growth mode, and with a different growth under different growth conditions. And in the shell, they first grow an N-type layer, then a quantum well, and then the P-type layer, and they form the PN junction for an LED. So each nanowire is an independent light-emitting diode, and as I said, by controlling the indium composition in that quantum well, that blue line, you can vary the color of the emission. So this is Osram's work. So I'll take I'll move a little bit before I go to the devices to the other nanostructure. The quantum dots. These are self-organized, three-dimensional quantum dots. And we were definitely one of the first groups to grow nitride quantum dots, and for sure the first group to make any device with these quantum dots. So what got me interested was these theoretical calculations which were done by one of my colleagues. And one of the problems in the LED world with the quantum well, all the quantum wells that are made and sold and commercialized and so on, the LEDs have quantum wells in the active region as the emitters. The one problem is that their lifetimes are very, very long. And so by the time a radiative recombination can take place to give out light, more often than not, the carriers go to non-radiative centers and are lost as phonons or heat. And my colleague did these calculations on a hexagonal pyramidal indium gallium nitride quantum dot on gallium nitride, and showed that the lifetimes in the dots, because these dots form by strain relaxation, and also because of and therefore the low polarization field, the overlap between the electron and hole is much stronger, and the lifetime is much shorter. In fact, the lifetimes are about 100 times smaller than in equivalent quantum wells. And this is what got me interested. So one of the first things we did was to measure the lifetimes. And so we started growing self-organized. I had about 20 years of experience in growing self-organized indium arsenide quantum dots, which are now being inserted in commercial lasers and amplifiers and so on. So we knew how to grow, although it wasn't that trivial to grow nitride quantum dots. But anyway, we started growing them, and I'll show you micrographs of those. But we measured the lifetimes, and indeed our lifetimes agreed exactly with what was being calculated, and they were indeed very, very small. So this is what got us started a few years ago, and our charter was to try and do things that could not be done with quantum wells, so these quantum dots, if they could be inserted in LEDs or lasers, they would obviously have much weaker polarization fields, therefore smaller blue shapes, and the localization of carriers in these three-dimensional quantum dots, the carriers would not wander away as they do in quantum wells and recombine in non-radiative centers. They would stay confined and recombine radiatively and give out light. So that was the premise. So this is what the self-organized quantum dots look like. They are typically about 2 to 4 nanometers in height. This is an atomic force microscopy image. We can vary their density all the way from 10 to the power 8 actually to 10 to the power 11 per centimeter square. And we've done all kinds. So they are kinetically driven, and this is a kinetically driven model of its this is a function, scaling function for the height of the dots, and it obeys a scaling law. And as we increase the temperature of the substrate, the I is the number of atoms, one less than the number of atoms that make up a dot. The value of I increases, and so it's kinetically driven. This is the phase diagram, the transition from 2D to 3D, and so you can see we are growing all our red dots and green dots and blue dots. By the way, we were the first ones to show any red color, red emission with the nitrides, and both with the nanowires and with the quantum dots. And here you can see the emission in the red and at room temperature. So now I'll start with some applications, and first I'll show you. This is a view graph I borrowed from Osram. So this is how Osram or Cree or Lumiled or any other lighting company, how they make the LEDs that you get to buy in stores. So it's not a red, green, blue combination, because as I said, they can't grow green and blue and green and red. So all they have is blue or violet LEDs. So what they do is, with these blue or violet LEDs, they excite yellow phosphor or red phosphor. And so what comes out is white light. Now there are problems with this technology. First of all, the phosphor technology itself is very complicated. The phosphors they don't have long-term reliability, and also in this conversion process, there is a loss. There's a large Stokes shift, there are reliability problems, and so on. But that's what you have to do. And so when you buy an LED, you see this huge package, most of it is this phosphor. And everything that is done to maintain and make this phosphor reliable. The LED is only a tiny blue LED, but nonetheless, that's what we have. And this is the chromaticity diagram for a commercial Osram-made white LED. And the color rendering index actually is not too bad. I mean, 100 is the CRI for fluorescent light, white light, and they are reaching 85, and that's pretty good. Now, what we would want is, of course, green, red, blue, or no phosphor. So this was. So once we could grow quantum dots that emit blue, green, red, and so on. So we said, okay, then let's make a converter dot, and we will use. So this is a simple LED PIN diode. There's the P and the N and so on. And in the N contact region, we put the so-called converter dots. These are passive. So these blue dots, blue emitting dots are excited. That light excites these red dots, and what comes out is white light. So there is no phosphor, no nothing in this. So this is truly a white LED, all semiconductor based. And what we have is tremendous flexibility, and we can tune, we can vary the emission wavelength of this, the number of these dots, similarly for these converter dots, and we can tune the output, and we can tune the color temperature and all kinds of things. So this is the chromaticity diagram, and on this diagram, as you see, white light is somewhere here in the middle, and you have warm white, which you use indoors, mostly in this part of the spectrum, and you have, as you go here, you go towards cool white light, as we call it, in this direction. And so we tried, we made different kinds of, different LEDs with different numbers of blue and red dots and slightly varying emission wavelengths. And you can see the color coordinate, the correlated color temperature correlated with the Planckian locus here. And just to calibrate you, Warm white light has a color temperature of about 3500 Kelvin. This is all based on Planck's radiation law. And what we got here, say for this LED, is somewhere between warm white and cool white, 4400. And this is a good temperature actually. And so these, you can see in these LEDs, the droop is much smaller. It's only about 15%. And so these are Osram is now taken over this technology, and they really are developing this in-house now for white LEDs. So that's a real application of quantum dots. Now let me move on to lasers. Now lasers with the nitrides is a very difficult technology. Now lasers, they are used in mobile full color projectors and laser displays, optical data storage, and I've given you some examples of applications here, medical and military applications, heads-up displays. This is a huge application area coming up. Some automobiles already have the high end, they have this as a standard feature. And I guess in the next decade, most cars will. Although I'm dreading this, you know, we try to dissuade people from texting and so on and so forth while you drive. You know what that leads to. And now we'll be looking at, as we drive, we'll be looking at all these things on the windshield. And I'm not so sure that I like that. But that's where it's going, and what they want is a red-emitting laser with a certain power, with a certain reliability, with a certain temperature of operation, which is pretty high, and efficiency and so on. And they don't have a red laser. Right now they use frequency conversion and all that. And in cars where you want that as a option, it costs about $2,500 to $3,000. And they want to, obviously. So we have a program now with Toyota Denso. They saw our paper on red lasers with these quantum dots, and they knew that nobody else can make red lasers. So they came to us, and so we are now developing red emitting lasers. Before that, of course, we made green and all that. So I'll just show you in one view graph some of the characteristics of a red edge emitting red laser. And so here are the quantum dots, 8 periods of those, and a standard diode laser configuration. Easier said than done. But here's the red emission of the laser and the light current characteristic, and you can see we are getting. They want 50 milliwatts, and we are getting there. The most important thing here is the threshold current density. Even in blue and green, the current lasers, nitride-based lasers made in the industry, have threshold currents which are 10 times this. And with quantum dots, we brought it down to about 1.7 kiloamps per centimeter square, which for the nitride system is very, very good. Because inherently, because of the high effective masses and the density of states and so on, you know that the density, the threshold current density is going to be large, but this is incredibly low in that context. Another application that which is very important now. There is no doubt in the silicon industry, in the CMOS industry, that there is going to be an optical layer where optical communication will take place. Some sort of WDM communication. And for WDM communication, what you need is a series of lasers with closely spaced frequencies. You need multiplexers, demultiplexers, and a waveguide, and of course, modulators, and then demultiplexers and photodiodes at the other end. Everything has been almost perfected. I've listened to recent talks both from Intel, from IBM, and so on. They have everything. One element, the most important element that they don't have is the laser. They just don't have a monolithic, low threshold, reliable laser on a CMOS chip. And this has been the holy grail for years and years. So what has been done in this context? So very early on, actually even before us, there is a person called Hadis Morkosh, was at Illinois, and he grew quantum well lasers, gallium arsenide based on silicon substrates. And this was the beginning. We demonstrated better lasers with indium arsenide quantum dots on silicon. The problem with this is that you cannot grow gallium arsenide on silicon. One is polar, the other one is bipolar, so you develop antiphase domains, and you just can't do it. So what we do is we have to tilt the substrate, and of course the CMOS industry is not going to build anything on tilted substrates. They want absolute 001. That's their preference, and that's how it's going to be forever. Then, this laser was demonstrated by forcing nature at MIT, germanium on silicon, a tensile strain germanium, and doping it to degeneracy, and they get a threshold current density of about 300 kiloamps. And then that laser is going to melt before it can do anything useful. And then you have this technology of from Santa Barbara, that they bond a high performance, let's say, 3-5 based laser onto the silicon wafer, and you can have the guiding either in the silicon by leaking the mode, or in the 3-5. That's a variation. The problem is the bonding technology and the long-term reliability of it. So that's the status. Now I think we now have the answer to that. So you saw that these nanowires, we can grow them beautifully on silicon. We made LEDs, and with this the Osram project, we were making these LEDs, both colored LEDs and white LEDs. So we knew how to make those devices with good reliability. So I told the students that, why don't we just think of the nanowires as a bulk material? Forget it's a forest of nanowires, and you process it and make an edge-emitting lasers. And of course, the first reaction is it's not going to work. We can't do it. So, go and do it. So think of just an edge-emitting Fabry-Perot laser, processed just like a laser. Here's the end contact, the P contact on top, and the light coming out from the edge. And of course, we put DVRs, which we do in most lasers anyway. And here's the laser heterostructure, multiple quantum disks. And the P-type, N-type, and so on and so forth. That's the mode profile. It's slightly more leaky than gallium arsenide or indium phosphide-based lasers, but so what? And there you are, beautiful lasers. So this is a laser on 001 silicon, very reliable. We actually measured the reliability, and the lifetime is roughly about 7,000 hours CW. And we even measured the modulation bandwidth, so they can be modulated, and so on. And there we are. And I'll talk more about this tomorrow. Let me move on to one other subject with the nanowires. As I said, single photon emitters are very important. So one way to get single photon emitters is to have a single quantum dot and have single photon emission. So one way to get a single photon dot is to have a single quantum disk in a very thin nanowire, and there you can see the micrograph of a single nanowire with a single disk that you can't see, and the two contacts. And of course, with that, you see this second order correlation. And what this is saying is that at zero delay, so what we have is the light coming out, the photons coming out, they go to two photodetectors through a 50-50 beam splitter, and we measure the delay of the arrival time of the photons, and we build a histogram. And of course, at zero delay, if the count is zero, then you know that you don't have two photons coming at the same time. And so here you see it. The problem with this is that a single nanowire with such a narrow diameter and so on, the resistance of the diode is humongous. And so it heats up a lot, and we can't get room temperature operation. So we went to the other nanostructure, the single quantum dot, and built a quantum dot LED. And of course, we just get the light from a single. These dots are very sparsely spaced, and there we got, in fact, the first room temperature single photon emitter, a visible single photon emitter. In fact, any single photon emitter working at room temperature with electrical injection. And these visible single photon emitters are very important for free space quantum cryptography. So there's a lot of demand now emerging from places like JPL and so on. And the last thing. So this is sheer fun. I mean, it started as fun, but now it's getting serious. So when you put an emitter, and I'll try to make it, I'll just skip the details and give you the essentials. So when you put an emitter, a photon emitter, in a microcavity, which is a resonator, then we normally work in what is called the weak coupling regime. And in the weak coupling regime, you can tune the emitter in and out of the photon, the microcavity photon from the cavity resonance, and you can either enhance the emission, which is the Purcell effect, or you can kill the emission. So that's the regime we normally work in. So the exciton is the emitter, and then you have the cavity photon, and you can tune them closer or further away, and you can either enhance the emission or you can suppress the emission. Now there is another regime of operation which is called the strong coupling regime, where this irreversible spontaneous emission process changes over to a reversible and periodic exchange of energy between the emitter and the cavity photon. And this period of exchange, the frequency of this exchange, we call it the Rabi oscillation frequency, it's larger than the decay rate of both the cavity photon and the exciton. That's the condition. The Rabi oscillation frequency is larger than the cavity decay rate or the exciton decay rate. And here, in the weak coupling regime, it's exactly the opposite. So, what happens in this regime, in the strong coupling regime, due to the coupling between the cavity photon and the exciton. And so there's an interaction between the photon field and the polarization field of the exciton. And as a result of that coupling, the normal modes of the system are not the cavity photon and the discrete cavity photon and the exciton, but there are these light matter entangled new eigenstates that form, which we call the upper polariton and the lower polariton. And these are the normal modes of the system now under strong coupling conditions. And they are separated by this characteristic energy, which is called the Rabi splitting. And if you excite the system very hard, I mean, this quasi-particle picture will disappear as you increase the excitation and cause a saturation when the detuning due to the polariton-phonon interaction exceeds the Rabi oscillation frequency, and then this quasi-particle picture of the polariton, and these polaritons are lost, and you get back to the exciton and the cavity photon. And the photons and the excitons, the cavity photons and excitons, they couple because the excitons are normally formed and they decay by a band, interband transition. Now, the eigen energies are given by these equations, and this is the Hamiltonian of the system. Now, what do we do with this? So if you look at this, the polariton dispersion relation, this is in K space, of course. So when we excite the system, we form excitons. From electron hole pairs, they combine to form excitons, and the excitons are scattered here by phonons. And these exciton polaritons, which are mostly excitons here, they are scattered by phonons and they come down. And at the same time, they're emitting photons also from the system, from the microcavity. And they come down by scattering. And then ultimately, if in any mode the population reaches 1, just like a normal photon laser, you have a a bosonic final state stimulation. Now the stimulated emission in a laser that we know of, it is also in general terms, it's a bosonic final state stimulation. So here, what we have is stimulated polariton scattering, and that quickly brings down the polaritons to form and this stimulated polariton scattering is the gain mechanism here. Just like stimulated emission is the gain mechanism in a normal laser, here the scattering mechanism is the scattering is the gain mechanism in this kind of thing. So it quickly forms a Bose condensate, which is a coherent condensate, not necessarily in equilibrium, but it can be at a temperature higher than the lattice, but it is phase coherent. And from this coherent condensate, we have spontaneous radiative recombination to give out light. So coherent light comes out by spontaneous emission, and therefore the energy required is much smaller than a normal laser, as you see. So the process of stimulation and emission are separated here. Whereas in a normal laser, the stimulated emission and stimulation and emission are one and the same process. Here, the stimulation process is this stimulated polariton scattering, which quickly brings and forms a phase coherent condensate here, and the emission itself is just spontaneous emission. It's actually a beautiful process. Anyway, all this was being unraveled by the physicists, and of course, a couple of them made the proposal that under the right conditions, you can actually see this coherent light, and so the race was on to make such a microcavity and show this coherent emission. And that was shown, and so on. So, but everything was very low temperature because they were using gallium arsenide microcavities, and as I showed you in the beginning, gallium arsenide has an exciton binding energy of 5 MeV, and so you could not use it at room temperature. So they were all at cryogenic temperatures. So here the first thing we did was took a single nanowire, we dispersed it and separated out, identified a single nanowire, buried it in a microcavity, and there you are. Here's the polariton dispersion measured now, and these are the upper and lower polariton luminescence, and here's the light current characteristic. So this is in the weak coupling regime. You see the polariton lasing, and the energy is 100 nanojoules per centimeter squared. It's incredibly small. Almost, so if you talk about a zero threshold laser, this is it. And then if you pump the system harder and harder, it goes to the weak coupling, and you see even in the same system, you can see normal photon lasing. And you see the difference in threshold is 3 orders of magnitude smaller in the same system. And finally, to make and of course the race was again, you want to get an electrically injected device. This is all optically pumped, and I have always believed that an optically pumped device is to understand the materials and the physics, but you really need, for applications, you really need an electrically injected device. And several groups around the world were working. So 2 years ago, we demonstrated the first electrically injected device, but that was working with gallium arsenide material, which is working at cryogenic temperatures. And that's no good either. You're not going to move around with a cryostat in real applications. So we had to make a real room temperature device. And here, I did something. This was again serendipity, I guess. Now, this whole community, they were fixated with a vertical device, that the light has to come out through the DVR mirrors, and it's a vertical VCSEL-like device, and so on. And I said, why does it have to be a vertical device? It can be just like an edge-emitting laser. So, and the problem with the nitride system is when you make a vertical device, the DVRs and so on add so much resistance to the diode, you just can't get anything out of it, anything useful. So I said, well, let's solve this resistance problem. So make the PN diode, PN junction in this direction,
and the microcavity in this direction. It's just like an HMAC. And the moment we did that, it became a very simple diode with a series resistance of a few ohms, as it should be. And there you are. We saw room temperature Polariton lasing. There's the Polariton lasing nonlinearity and the